Hi, physics students. Today we're going to talk about harmonics and beats. And in the last chapter, we talked about standing waves and how you can make waves. You know, if you have one person standing here and one person standing here, and you shake the spring or the string up and down, you can make a wave that just appears to be going up and down here with no motion at the ends. We call it the middle a node, or I'm sorry, an antinode, and we call the places of no motion the nodes. And if you shake it at twice the frequency, you can get two antinodes. If you do it at 3 times that initial frequency, you can get 3 antinodes, and so on. The lowest possible frequency that you can have is where the wavelength is equal to twice the length of the spring or the string that you're using. So look at this top one right up here. This is half a wavelength because it's either a crest or a trough at any one time. And a wave has to have a crest and a trough. So we call this the fundamental frequency. This is the simplest standing wave that you can make on a vibrating string. All right, now all of those other examples that you saw beneath that picture, those are what we call harmonics, and they're integral multiples of the fundamental frequency. And so the fundamental frequency is what we call the first harmonic, also known as F1 or F sub 1. The second harmonic we call F2, and its frequency is just 2 times whatever F1 was. And the third harmonic is F3, and that's 3 times what F1 was. And again, so on down the line. Whatever harmonic I want, I just multiply, if I want the 10,000th harmonic, I multiply it, the fundamental frequency, by 10,000. All right, so you might be saying, what does this have to do with anything? And the fact that you could probably leave the room and hear me talking and know that that's Mr. Lynchide talking is because of the unique sound quality that harmonics bring to the different things that we hear. Why does a trumpet sound the way it does? Why does a violin sound the way it does when they're playing the same notes? And it has to do with these added harmonics that are a part of the sounds and the vibrations that are made. That different sound quality that you hear is what we call timbre. I know it's spelled timbre, but you say it timbre. And it's the musical quality of a tone resulting from the combination of the harmonics that are present at different intensities. And like I said, a human being can sing the note C, and you can have a trumpet play that note, and you can have a violin play that note. And while you hear the same pitch, they all sound very different because of the fact that it's not just that one pure tone that is being made. And without timbre, without these other harmonics, everything would sound like tuning forks talking to each other, and it'd just be very dry and sterile and odd. All right, so here's an example. Here you have 2 waves that are being made at the same time. You've got the blue wave right here, and then you've got the third harmonic. That blue wave is the fundamental, kind of the simplest one that you can have. Then you've got the third harmonic. Notice that here for the fundamental, there's just one crest. So that would be that first picture I showed you. But then down here, we've got 2 troughs and a crest. So 3 antinodes, here you have 1 antinode. So the third harmonic. Now, if those 2 tones are played at the same time, it won't be 2 different sounds. They're going to mix into one sound, and that's represented by the red line. So you can see here that this crest and this crest add together to give the wave the amplitude up here at the red. And you can see right here, there's no amplitude on either the third harmonic or the fundamental, and therefore the red wave also has a value of 0 at that point. And look at that red wave. It's also not a nice, smooth, perfect cosine or sine wave. Okay, there's a little hitch in it right here, and then it comes down, and that's going to just continue to repeat. That is a very simplified example of how this all works. The fact of the matter is there are many harmonics that are at play and that add together when particular instruments or particular voices or particular vibrations are made. And so this is the wave pattern that is formed for 4 different instruments, all doing the same thing. And you can see that, again, some of these do not even look like they're cosine or sine waves at all. But nevertheless, that's why these all have unique sounds, putting lots of different harmonics into combination with one another. Now, when you play a note on a string, fundamental frequencies played along with some of the harmonics. And it's interesting, you can go ahead and watch this video if you want to, but basically you can make these videos. I've done it, but you can take a phone and stick it right inside a guitar. You just have to have the light coming toward it. But when you pick the different strings, you can see the waveform on the string itself, and it has to do with the frame rate that a video, like an iPhone or a smartphone, video's at. But it's pretty cool. So I would watch that if I were you. This is another very good explanation of how harmonics are put together. And they use different instruments, and you can see the waveforms. It's about 10 minutes long. But again, I think it's pretty interesting. This video right here, this is on why it's hard to tune a piano, and this kind of takes you down the rabbit hole of how do we tune instruments, and why are the notes that we call, A, B, C, D, E, F, G, how did we assign different frequencies to them? And if you look into how tuning is done, there are a few different ways, but people can devote their life to figuring out how this stuff all works. But again, kind of just very interesting. If you're somebody who's into music and maybe you're in band or choir, you know that there are certain notes that go together. You can't just randomly sit down at the piano and just start, cranking on the keys. There are certain ones that go together. And so the question is why? Why is a C chord, which is the note C, E, and G, why do those 3 notes work together? Well, G is the 3rd harmonic of C, and E is the 5th harmonic of C. And so those notes are just multiples of the original. So yes, they do go together. All right, this is super interesting on auto tune and how they voices are fixed, and this is just kind of fun. So mathematically, using the wave speed equation, we know that velocity equals frequency times wavelength, and we're putting wavelength in as 2 times the length of the string. So this is lambda, but we changed it to 2L. And so if we rearrange, we know that the frequency is the velocity divided by 2 times the length for the fundamental frequency. Now, in general, for any frequency, it's, if I want the 2nd frequency, I'm going to put a 2 in front of this. And you can have any integer you want for a string. So V is the speed of sound in a string, L is the length of the string. Now, for air columns, so like I'm talking about like a pipe organ and that kind of thing, standing waves occur with sound. It's not, or with the particles of the air. And so if you open up this, it shows you and maybe if you're using a Chromebook, it's going to tell you can't do it because it's on flash. But you can see the waves going back and forth. And even with this open pipe here, you still get a reflection. Now that reflection is inverted in an air column, but nevertheless, that's what a wave looks like in an air column. And when I talk about air column, again, I said pipes, but flutes, clarinets, oboes, those same sorts of things. Right? In an open tube, a tube that's open at both ends, the equation for figuring out frequency is the same. So any frequency you want, any integer whole number will work, right? And the speed of sound is your velocity. So it's a little bit different than a string, because a string can have very different velocities depending on the material the string is made of. L is the length of the tube. All right, so here's the standing wave in a tube. What does that look like? That's this right here. And again, that's something you could probably stare at for 2 hours. But again, you've got areas where there is no motion. This red dot right here. And then you've got some areas where you get the maximum amount of motion. And that again is called the antinode. This first red dot is called the node. And here's another way to look at that. You know, if you're not thinking about the particles kind of doing the accordion thing. Here you've got your node. So in an open tube, this is different from a string. In an open tube, you have two antinodes, and you have a node in the middle for the fundamental frequency. Okay, for a string, it's the opposite. Because both ends of the string have to be nodes, you have one antinode. So here, I mean, we have an antinode at the end and an antinode at the end. Same thing, you know, if I start increasing the frequencies, I still always have antinodes at the ends of the tubes. Again, that's the opposite of strings. Now, if you have a tube that you close at one end, suddenly you can fit a fourth of a wave in, right? You can have an antinode at an open end, but you have to have a node at the closed end because the particles of air cannot move there. That changes our equation, and it changes a few like real world things about the notes that can be played. Because one end has to be a node, only odd integers are going to be available. And so that changes our equation to Fn equals Nv over 4L. And so N can only be 1, 3, and 5 now. Remember in the other two equations, it was 2L. Now, the other thing here is you can make pipes that are half the length of open tube pipes and get the same notes out. It's just that the harmonics are not quite the same. So the sound quality is going to be a little bit different. Maybe not super noticeable to the untrained ear, but some people can definitely pick out those minute differences. All right, that's it.